Welcome to the first video on integration. We're going to go over some concepts and intuitions behind how integration works, what an integral is, when to use them, and the fundamental theorem of calculus. So let's take a look at an integral and remind ourselves what all the bits are. So if I write down big F of x is squiggly line AB, little f of x dx. That's the standard form of an integral. So what are all the little bits? Let me say that big F of x is the integral over x of the smaller function f of x in between x is equal to a and b. So big F of x is the integral. Little f of x is the integrand, the function that we're integrating. Dx is the differential. You can think of that as being equivalent to the dx that's in Leibniz notation for derivatives, in that it tells us what variable we're integrating with respect to or over. Usually we say we're integrating over x. And it also is an infinitesimally small interval of delta x. And then finally, these guys, a and b, are the upper and lower limits of our integral. If they're not given, then it's an indefinite integral, and you just assume you're evaluating it for all possible values of x. And if they are given, a is the lower limit, b is the upper limit, and you're evaluating the integral for values of x, greater than a and less than b. So now into the bits of an integral, what do they actually do? Okay, so now that we know what the bits are, it still remains to be said of f of x, my integral of little f of x dx between a and b, say. What does that actually mean? I have a wise colleague who often says to scared-looking undergraduates when they first get a look at his waddling work, "Don't worry, mate. Integrals are just fancy sums." I used to live in New Zealand. Everybody calls everybody mate. And so integrals are often introduced with this intuition of the area below a curve. So if you think of the dx in your integral as being equivalent to delta x, some change in x, then by definition, the integral really is computing the area under a curve, which is a visual, so I have to draw some ugly graphs here for a minute. So let's say I've got my x and my y. I guess they should go off this way too. And some function. Actually, no. The simplest kind of area under a curve would be a horizontal line. Y is equal to 3, say. And if I want to calculate the area under that curve in between x is equal to 1 and x is equal to 5, then I just say, well, the height of my curve is 3, f of x. It's 3 everywhere. And my change in x is 5 minus 1 is 4. So my area here is 3 times 4 is 12. That sucked. Let's try that again. The simplest curve to find an area under is just a straight horizontal line. Let's call this one y is equal to 3. And I want to know the area under the curve between x is equal to 1 and x is equal to 4. Well, the area in question is just a rectangle in here. So I want to know the area of that rectangle. Well, I want to know the change in x, which is just 4 minus 1 is 3. And the height of my area is just 3. So area is y times x is equal to 3 times 3 is 9. Those are multiplication symbols. I'm used to just using a dot. But what if I want to know the area under a more complicated looking curve than just a rectangle? Let's make all this go away. Now let's say I have a fancier looking curve, something like this, which is f of x here. If I want to know the area under the curve between s is equal to 1 and x is equal to 4, we can imagine well, I could approximate it using just this point and get a rectangle like this, and that would be way too small. By saying my change in x here is 3 and my value of my function here is 1, so I'd get a 3 by 1 area here, and that would be wrong. And I could use this function, I could use this value, I could say, well, if it's, I could approximate it as this rectangle, and that would be differently wrong, but still wrong. We can imagine defining some delta x smaller than my total x. Let's set dx is equal to 1. So I'll evaluate my function at 1 and 2 and 3 and 4, and then I can draw a rectangle here, and, whoops, here, and here. So my area here would be my sum from x is 1 to 4, or I guess 2 and 4 I should say, because we're using these values, 2 and 3 and 4, to make our rectangles, of the function of the value of the function at x times dx, the change in x. And you can imagine if you make the interval smaller, then you'll get more rectangles. Right? And the area will get closer to the real area as you make the rectangle smaller and smaller and smaller and smaller and smaller and smaller and smaller. Tiny, 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 tiny rectangles until your approximation gets really good. So you can think of the integral of f at x as being kind of like the limit as dx goes to 0 of a fancy sum of the function of x times dx, your differential. And in fact, if you look at the integration symbol, it looks like a stretched out s for a reason. It was originally intended to represent a kind of fancy sum between the limits a and b of the function value at x times the differential. But what about indefinite integrals? If I have an integral, let's say big f of x, that's an indefinite integral, there's no a and b, there's no limits of my function, then the area intuition kind of breaks down for me, because if I have a continuous function, right, and it presumably goes off to infinity in either direction, then the area under that curve for all values of x has a little bit less meaning, because if x goes off to infinity in either directions, it's possible for the area under it to be infinite, even if it's not actually. It gets sort of waffly about the area under a curve thing, for me anyway, intuitively. So for indefinite integrals, I tend to think of them by the other sort of definition of integration, which is that integration is the opposite of differentiation, which is why antiderivative is a synonym for indefinite integrals quite a lot of the time. Quite simply, and if you want to know the value of an indefinite integral, you just have to ask yourself, what function does it look like it's the derivative of? By that I mean, if the integral of little x, so if big F is the integral of little f, then that means that the derivative of big F is equal to little f. Which also means that if I have the derivative of fx d of x, and I want to take the derivative of that whole thing, it's just going to give me back f at x. So integration and differentiation are kind of opposite operations, like multiplication and division are opposite, or addition and subtraction are opposite, just in a fancier sense of opposite. Which brings me to the fundamental theorem of calculus, which has two parts. And I'm not going to go into big detail on proofs. If you would like proofs, I'm going to put links to them here. The first part of the fundamental theorem of calculus basically states, if we set big F of x to be the integral of little f of x dx, then, as I said before, the derivative of big F is little f. This is really important to remember, and I can't stress it enough, that if you take the derivative of an integral, you get the original function back. If you integrate a derivative, you get the original function back. They are opposites. For example, using some functions I find easy to think about, if I define little f of x to be the cosine of x, then the integral of the cosine of x is just sine of x. Because, if you recall, the derivative of sine of x is the cosine of x. Alright, I just knew that that was the integral. I didn't do any magic calculations. But wait, there's a problem. I admit I tend to forget about this, but it's very important. The indefinite integral of cosine x is sine of x plus some constant c. Why do I need to put a constant in there? Because if you think about it, what's the derivative of sine of x plus 3? Well, that's cosine of x. How about the derivative of sine of x minus 273? Well, that's also cosine of x. So as it turns out, any function that is sine of x plus something is an antiderivative of the cosine of x. Because constants disappear when you differentiate, the going back and forth between differentiation and integration in the indefinite integrals requires you to add this constant of integration when you take an indefinite integral, because each function has a family of an infinite number of antiderivatives that differ only by the value of their constant of integration, c. Sometimes in practice you'll go and take another step to figure out what your particular value of c should be for your function. Other times you can just ignore it, but it's important to remember that while definite integrals only have one solution, indefinite integrals have an infinite family of solutions that all just differ by c. Speaking of definite integrals, the second part of the fundamental theorem of calculus has to do with definite integrals and how we evaluate them. So remembering a definite integral is just an integral that has bounds a and b. So you're interested in the so-called metaphorical area under the curve in between x is equal to a and x is equal to b. It turns out the way to evaluate that is just the value of the indefinite integral at b and the indefinite integral evaluated at a, the difference between them. So the value of the whole integral between a and b is just the value of the integral at b minus the value of the integral at a, which you're either thinking, oh, that's totally obvious, or you're thinking, what? Please prove that to me. So the proof of this second part of the fundamental theorem is actually quite simple. A simple proof of this comes from the fact that we can define another integral g of x, which is just the integral from a to x of f of x dx. So by virtue of the infinitely many antiderivatives, there must be some value of x for which f of x plus c is equal to g of x. Right, because all the antiderivatives of our function little f of x differ by some constant amount. So that's our c here. So now I'm going to define at a the integral between a and a of f of x dx. Well, that's g of a, which is also f of a plus c, which is also equal to 0. So if f of a plus c is equal to 0, then c is equal to negative f of a, which we can go back to the very beginning and say if g of x is equal to f of x plus c, then it's equal to f of x minus f of a, which looks a whole lot like this if we replace x with b. So this is a great and tremendously useful thing, because it means that whenever you have to solve a definite integral, you just first find the antiderivative at b and the antiderivative at a, the upper limit and the lower limit, and subtract. By now you're probably wondering, this is great, so I know what an antiderivative is, I know what my fancy sum definite integral is, but how do I actually solve them if I have a problem set in front of me or if I'm trying to make a model? How do you evaluate integrals? And in fact, this video is not about that. There's a whole set of tools that I'm going to talk about elsewhere. Maybe I'll even put a link in. Right. But the fact is, unlike differentiation, where there are handy algorithms and rules that tell us how to differentiate a function, there aren't really those for integration, other than the fact that it's the opposite of differentiation. So it has been said that where differentiation is a science, integration is an art. So it takes practice, and you see your function and you say, well, what does that look like? It's the derivative of. So that's kind of the bad news, is that the way you solve integrals is by just knowing or having ways to guess at what function they are the derivative of. I'm just going to do an extremely short example of solving a definite integral. So let's say my big f of x that I care about is the integral between 1 and 3 of a function defined as negative x squared plus 4x dx. Well, the first thing I need to do is to solve the indefinite integral, ignoring the 1 and the 3 of just negative x squared plus 4x. And this is where we play the backwards game of what does that look like the derivative of. So the derivative of negative x squared is going to be something negative, and it's going to have an x cubed. And since I don't want there to be any coefficient, then I divide by 3, because if I take the derivative of this function, the 3 is going to come down, cancel with that, and this will come down to a 2. So there's that term, and the antiderivative of 4x is going to have an x squared, and it's going to have, we want it to be 4, so it'll be 2 plus. And so checking that, the derivative of 2x squared, the 2 comes down, becomes a 4, yes. So that's my indefinite version of this integral. So at 1, f of 1 is going to be negative 1 over 3 times 1 cubed plus 2 times 1 squared, which is 2 minus a third, which is 1.67 or so. And the function at 3 is negative 1 over 3 cubed, plus 2 times 3 squared, which is going to be negative 9 plus 18, which is 9. My solution up here is going to be f of 3 minus f of 1, which is equal to 9 minus 1 2/3, which is 7 1/3. Since it totally looks like I just made that up, let's take a look at the function itself and reassure ourselves that that does in fact give me the area under the curve. So this function, there's my y and my x. 1, 2, 3, 4. So this function is actually a reverse parabola. It goes kind of like this. And I wanted to know the value between 1 and 3. This area here. So at x is equal to 1, my original function is minus 1 plus 4, which is actually 3. At x is equal to 2, well, my scale is off. At x is equal to 2, the function is a value of 4. So if we approximate this, we're going to get 3 times 1 plus 4 times 1. And a very, very basic approximation is going to be 4 plus 3, which is 7. So a better approximation with more intervals, as I fill this in, is just going to get closer and closer to the real value of 7 1/3. So the handy thing about this integration being backwards differentiation is you can always check your answer by, if you think, just like I did back over here, if I think the integral should be 1/3 x cubed, I can just quickly take the derivative and make sure I get back my original function. And at last, reminding you why you should care about taking the area under a curve or doing backwards differentiation is that integrals are one of the most important tools in all of modeling, actually, in part because of it allowing you to go backwards and forwards with derivatives. For example, in population biology in particular, you often know population growth rate, and the integral of that is population number. So if you have some function that tells you population growth rate, you can integrate that function to find out the population size at some given time, which is handy. Similarly, anytime you have a rate of change, like you might know allele frequency change, take the integral of that, you can get allele frequency. And then the obvious area under the curve is probability distributions. Because if you take the integral of a probability distribution, it actually gives you the probability at the limits of your integral. Or the probability of the event that's happening in between the limits of your integral, I should say. We'll talk more about that in the probability videos. And similarly, if you've got mortality rates, take the integral of that, you get total mortality. The overall trend here, right, is you've got some function that gives you a rate of change, and integration gives you back the original function that measures the thing that was changing. So thank you for listening, and in the next video I'll go over some tools and algorithms to help make solving integrals a little bit less painful.